to Kadam Academy YouTube channel. Friend, under this vibration examples, various examples I have taken. This is the shaft spring in series or parallel numerical based on this one. Okay. For this transverse vibration, this is also case related to transverse vibration. We will also study in few videos transverse vibration, torsional vibration. In this case, the example is given to you. Find the natural frequency of the mass. Here this mass is there. For the system shown in this figure 1, neglect the mass of cantilever. This mass we have to neglect. This is the cantilever beam. Dark line shown because it is a beam with some cross-sectional area, and it's a material with the modulus of elasticity E, capital E, and its a mass moment of inertia Ix is given to you with length L, and here this free end and it's a fixed end. At the free end, the K is the spring stiffness. Attached to the spring is mass M, and this is the displacement shown X. Okay, so what we have to do? We have to find the natural frequency of this mass M system shown. Neglect the cantilever. Okay, so in this case, what is the given? Mass moment of inertia Ix is given, modulus of velocity E is given, spring stiffness K is given, mass M, displacement X, and the length of cantilever beam L is given. What we have to find out? Omega n we have to find out. Here also the two case studies, some case studies, special case we have to consider. Study in special case when K is infinite and Ix is infinite. This K is infinite in one case, or what will happen when the Ix is infinite? This Ix is infinite. So these two cases we also have to study in this numerical. Friend, we'll solve this numerical now. So here, what will happen? Cantilever beam, when it will, this cantilever beam, when it is displaced, this mass is having self-weight, it is a static deflection. After this displacement X, this also some deflect with the some, you can show here, deflection delta. Here, this delta, that we have to find out here. That cantilever beam deflects by this delta, and the delta we can write by using this. We already studied in last one of this transverse vibration video. You can see the whatever the value, standard values for the beam, various case, okay, various conditions. The value of delta is also given to you that in that tabular form. So this is already you have studied in strength of material. That value for this del means deflection WLQ under this in denominator 3 into EIX. Okay, this is the deflection. This is the deflection of this beam. Next, what we have to find out? This beam we are here consider. This is the KT. This is the what we are doing? We are considering this beam as a spring. In this case, we are considering this beam behave like a spring. It will have deflection del. In this case, K is spring and deflection X. So this beam with we are considering its stiffness K1, and this spring is there with stiffness K. So these springs are in series. So its equivalent spring stiffness we have to find out. But before that, value of K1, how to find out the value of K1? So therefore K1 is equal to, you can find out by using this formula, this W upon this del. What is the W? W is the weight attached, weight of this total body, and the upon del. So this the force, that means it's not only weight, it is total force applied at this end of this beam. W is the force applied at the end. So we can write W by del is equal to W by, we'll put this value of del in this here, WL cube 3EIX. So what is the value of K1 then? Then the value of K1, I'll write here 3EIX in denominator. What is the value? Become till the L cube. So this is the value of K. Now in next step, what we have to find out? Actually we have to find out the omega n. To find out the omega n, we required this K equivalent. K equivalent is required. Why? Because we know this, the formula for this omega n, that omega n becomes, we can K by m. K by m. What is K in this case? Suppose this, you consider this case we are considering, this is the spring mass system. In this case omega n becomes under root of K by m. But here K is K equivalent. This K equivalent we have to find out. To find the next step is what? To find equivalent spring stiffness, that is K equivalent. So this K equivalent, as these two springs are in series, so we can write here K equivalent, which is equal to K1 plus 1 by K. Correct? Because the springs, these two springs, it will in series. This formula for the spring is series. So I'll write here 1 by K equivalent is equal to L cube. Put the K1 value here, 3EIX plus 1 by K. So again, just rewriting this K into L cube plus 3EIX here. To find the spring stiffness, K equivalent, 1 by K equivalent is equal to 1 by K1, 1 by K, spring in series. So K equivalent is equal to this, putting this value here and in denominator, so it will go, this L cube will go top side and this come bottom side. So what will happen then? 1 upon K. So just solving this equation and rewriting this equation, KL cube plus 3EIX, okay, EIX, denominator, what will the denominator? 3 times EIX into K. Okay, so this is the K equivalent when it is 1 by K equivalent. So K equivalent becomes reciprocal of this one, that is 3EIX K, denominator KL cube plus 3EIX. So K equivalent, once we find out by what is the formula for this, finding this omega n for the spring mass system, we know this omega n is equal to under root of K by m. So K equivalent is, we have to put the value of in here K equivalent, we will get the omega n is equal to under root of, again we have to write this value of K, and in denominator only we have to add m. Okay, so this 3EIX K. Inside the bracket I will write this one, KL cube plus 3EIX into M multiplied by M. So this is what? This is the omega n. Value of omega n. Now what we have to find out? We have to find out this frequency, natural frequency, the Fn. Fn we have to find out. Fn we can find out by using this formula, omega n by 2 pi. So we have to find out Fn. I'll write again this equation. This put the value of here, this omega n in here, 3EIX K denominator KL cube plus 3EIX into M. So friend, this is the answer. Okay. Ask in this numerical. What is asked in this numerical? This omega n and this Fn we have to find out. Natural frequency of this mass we have to find out. So we have to find out this natural frequency and frequency of oscillation. We have written the equation for this. Okay, but in this case, this case 1 and case 2 are remaining. This were solved. This also were obtained. These two were obtained. We are now go for this one. Okay. Now the case 1, if this k is equal to infinite, here in this case the k1 and k2, these two values are there, and just in putting this value of k here infinite in this equation, what will get? See, I'll write again that equation, 1 upon k equivalent is equal to 1 upon k1 plus 1 upon infinite. That is the, as k is equal to infinite. So what will happen in this one? This term becomes 1 upon k becomes 0. That term becomes 1 upon, which is equal to 1 upon infinite becomes 0. Value of this one 0. So this is 0. So we can write here from this k equivalent is equal to k1. Okay. So what is the value of omega n then? When k equivalent is equal to, so the omega n becomes, I will write here k1. K1 means what? That value here value of this equation, this value will get changed. So omega n becomes k1 divided by m. Okay. So what is the value of k1? The k1 we already were solved here. The value of k1 is 3EIX L cube. Here 3EIX L cube into this m. So this is the omega n. Okay. When this is natural frequency when the k is infinite. Next case is what? Next case 2, you can say case 2 here. The case 2, if this k1 or what is the given? Ix is infinite. This mass moment of inertia, here it is given Ix is infinite. This mass moment of inertia, this Ix for this beam is infinite. Value of Ix is infinite. So what will the answer? We'll see. These two cases are there. This were studied. This were in case 1, when k is infinite in that numerical, so that becomes this. I will show you. This is the your cantilever beam, and here this spring, this mass m, okay, it is displaced by x. So this k and this is the k1. This is, it will represented. These two springs are in series. Okay, this is the k and this is the k1. when this k is infinite, this system becomes like this. This system, the cantilever beam with the weight is placed at the end with mass m, it will be look like this. This will be converted when, in this case, its omega, natural frequency becomes omega n. Okay. We are going to study here case 2. When this Ix becomes infinite, so what will happen? This is the case 2. In this case, the value of Ix is infinite. We have to utilize this k equivalent, same formula, 1 upon k1 plus 1 upon k. Okay, that was already written here. And this value of k1 we know, 3eIx divided by L cube. This we already derived. If this k1 is infinite, okay, that means Ix is here infinite. Ix is infinite. So in this case, when k1 is infinite, when Ix is infinite. See, this is the formula. Just put the value of Ix here. Just putting the value of Ix here infinite. Here Ix is, when Ix is infinite, automatically k1 becomes infinite. So when this k1 becomes infinite, is equal to 1 upon infinite is equal to 0. Correct? So friend, here this term becomes 0. Okay. Then ultimately k equivalent is equal to 1 upon k. 1 upon k means that is the stiffness of spring, and this will represent what? The k equivalent is equal to k. So we can say this system become now a simple spring mass system with the stiffness k and mass is m and displaced by x distance. So what will its frequency then? We know, all of we, this k by m, simple frequency is where 100. So this is the case 2 answer. This is the answer for the case 2, and already we have studied the case 1 answer here. So friend, like this, solve this numerical, very simple one. Okay, with the different case. When we consider this as a, so it is fixed one. Infinite Ix means mass moment of inertia is infinite, it means it's fixed. Only this spring and mass will be there. So this omega n becomes k by m. That will represent, now it is fixed one, like this one. This fixed single spring mass system will convert into that one. So this is the numerical. Friend, if you are till now you are subscribed my channel, please subscribe my channel. You will get more and more practical videos later on. Okay, so also click on the bell icon. Thank you very much. Kadam Academy.